Before we get started in acid and base chemistry, let's just do a quick recap on equilibrium. So recall that a process that is in equilibrium has a forward reaction where the reactants are moving to products, but it also has simultaneously the reverse reaction of the products reforming reactants. Both of these reactions happen at the same time. Once they reach equilibrium, we say that the rate of the forward reaction is equal to the rate of the reverse reaction. From here, we can set up the equilibrium constant expression, capital K. K, or in this case, KEQ, equilibrium constant, is equal to the concentration of the products over the concentration of reactants. So for a generic reaction, we can see that for reactants going to products, the equilibrium constant based on concentration is equal to the concentration of each react product raised to the power of the coefficient to that product over the concentration of each reactant raised to the coefficient with respect to each reactant. Now remember that in the case of having a pure liquid or a pure solid, that we translate those into the equilibrium constant expression as 1. So you can see here that we have two aqueous products, their concentrations in there, raised to the first power. And here our reactant is aqueous, we see it there, acetic acid, and 1 for the pure liquid water. So ask yourself this question: which of the following statements is the definition of a Bronsted-Lowry acid? Now, I do trust that you have done a little bit of reading before you start watching these videos. If not, go ahead and take your best guess. The answer is that a Bronsted-Lowry acid is a proton donor. So let's review some of the basic definitions of acid. So the original definition of an acid came from Svante Arrhenius. An acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions, think hydronium. And a base is a substance, when dissolved in water, increases the concentration of hydroxide anions. In the Bronsted-Lowry definition, an acid is a proton donor. The acid must have a removable acidic proton or acidic hydrogen that gives off H+, and that a base has a lone pair of electrons that accepts a proton. So we know that acids produce hydronium cations in aqueous solution. Some of the other common properties of acid are that they turn litmus from blue to red. They react with some metals and form hydrogen gas. They react with base to form salt and water. They have a pH less than 7, and they have a sour taste. Some acids that you might be familiar with include hydrochloric acid, HCl, which is active in your gastric juices, sulfuric acid, H2SO4, which is a major component of car batteries, acetic acid, do you see the acidic proton here, which is in vinegar, and citric acids and tartric acids, which are used on the coating of Sour Patch Kids. Sulfuric acid and hydrochloric acid are known as mineral acids, and you also know these as being two of your strong acids. Look at these organic acids, these carbon-containing molecules, where the acid or acidic proton comes in the form of a carboxylic acid functional group, where you see that carbon-oxygen double bond with that carbon also having that OH group, and it's that acidic proton in that OH group which accounts for these being acids. Bases, on the other hand, produce hydroxide anions in solution. Chemically, they're opposite of acids. They turn litmus from red to blue. They taste very bitter. In solution, they often feel slippery. pH is greater than 7. A key point to understand here is that acids and bases react with one another, sometimes quite violently. So what happens when we dissolve an acid into water? We take the example here that we have of hydrochloric acid and water. We know that hydrochloric acid is a strong acid and it fully dissociates into the chloride anion and hydronium cation. The Bronsted-Lowry acid, hydrochloric acid, donates the proton to the lone pair of electrons on the water molecule, which is acting as the Bronsted-Lowry base, or the proton acceptor. So in this Bronsted-Lowry acid-base reaction, we have the Bronsted-Lowry acid donating the proton to the Bronsted-Lowry base. The Bronsted-Lowry acid, after it donates the proton to the base, forms a conjugate base. So the conjugate base of the Bronsted-Lowry acid is down 1H plus, or 1 proton. The Bronsted-Lowry base, which accepts that proton, forms a conjugate acid of the Bronsted-Lowry base, or in this case, the hydronium cation. Some molecules can act as a Bronsted-Lowry acid or a Bronsted-Lowry base. They're known as amphiprotic. In this case, we can see these molecules acting as Bronsted-Lowry acids, or proton donors. So here we can see each species acting as a Bronsted-Lowry acid, donating a proton to the corresponding base, forming a deprotonated acid, or the conjugate base of the original Bronsted-Lowry acid, and then the base, which accepts the proton, forms the conjugate acid of that Bronsted-Lowry base. On the other hand, if our species are acting as a Bronsted-Lowry base, or a proton acceptor, they can accept a proton from an acid, protonating them, and forming the anion of the acid. So in this case, each species, the original Bronsted-Lowry base forms a conjugate acid, and the Bronsted-Lowry acid forms a conjugate base. So let's clarify this idea of Bronsted-Lowry acid and base conjugate pairs. What does this mean? So a Bronsted-Lowry acid is a proton donor. And when we talk about a proton donor, we're talking about that hydrogen ion, that H plus, right? So the Bronsted-Lowry acid is going to donate an H plus, and a Bronsted-Lowry base is going to accept the H plus. The result is that one molecule gives up an H plus, one molecule accepts an H plus, and we form new molecules. Let's look at the reaction below with nitrous acid. So in the case of nitrous acid, we have our acid, our Bronsted-Lowry acid, HNO2. It's going to donate a proton, right? When it does so, it donates that proton to the Bronsted-Lowry base. In this case, water is acting as our Bronsted-Lowry base. So that acid, the Bronsted-Lowry acid, removes the proton, and what do we have left over? We have the molecule with one less H plus to it. This is referred to as the conjugate base. It is the conjugate base of your original Bronsted-Lowry acid. On the other end, you've got a Bronsted-Lowry base. Okay, so water accepted the proton from our acid. When it accepts the proton or adds that H plus ion to its molecule, it forms what we call a conjugate acid. So the conjugate acid comes from the original Bronsted-Lowry base. So what we have now are two conjugate pairs. We have our original Bronsted-Lowry acid, HNO2. It donates its proton and forms a conjugate base, nitrite, NO2 minus. That is one conjugate pair. We have a Bronsted-Lowry acid, and we have its conjugate base. We also have our original Bronsted-Lowry base, water. It accepts a proton to form hydronium, and we've formed another conjugate pair. Here we have our original Bronsted-Lowry base, and its conjugate acid. Notice that the only difference in any conjugate acid-base pairing is the acid has the H plus, the base doesn't have it. The base doesn't have it, the acid does have it. Okay, so let's practice this a couple of times. Here are a few problems that I'm presenting to you. So what I want you to do is take a look at these problems, answer, give the conjugate base for the following Bronsted-Lowry acid. So we are defining these molecules as acid. And then give the conjugate acid of the following Bronsted-Lowry bases. So we are defining Bronsted-Lowry bases. So your acids will be proton donors, indicate what their conjugate bases will be. Your bases will be proton acceptors, identify what their conjugate acids will be. Go ahead and hit pause now. No, hit pause, write down these answers, and I'll give you the solution here in a second. All right, so here we go. So a Bronsted-Lowry acid is going to donate or lose an H plus ion. Now notice that we're losing a charged species here, and we have to conserve charge. So when this organic acid donates its H plus ion, what's left behind is minus one H plus ion. So we get this formula here. We have a Bronsted-Lowry acid and its conjugate base. With the case of hydrogen phosphate, it is also going to donate or lose one H plus from its molecule, and resulting behind is its conjugate base, or the phosphate anion. Again, notice that when I go from a -2 charge as an acid, I lose that H plus, I result in a -3 charged species. For our Bronsted-Lowry bases now, the proton acceptors, if carbonate accepts or adds one H plus ion, right? We're going to add that to the molecule. We get bicarbonate here. Notice the difference in charge, right? You start with 2 minus, you add an H plus, you go to HCO3 minus. Now these nitrogen-containing compounds can be a little tricky. Remember, you need a lone pair of electrons to accept that proton. So you're not going to add it to this portion of the molecule. You're going to add that proton to the nitrogen. You add that proton to the nitrogen, to that amine, and you become an ammonium cation. So let's look at a couple of Bronsted-Lowry acid-base reactions. So what you're asked to do is label each species in these reaction equations as the Bronsted-Lowry acid, the conjugate base, the Bronsted-Lowry base, and the conjugate acid. Go ahead and hit pause, and I'll be right back with the answers. So the first thing we need to do is identify either which molecule is donating a proton or accepting the proton. In our first reaction, we can take a look at water. Water is pretty easy to spot. And we can see on the product side that water has gained a proton. That means that water as a reactant is going to serve as your Bronsted-Lowry base or your proton acceptor. That makes our other species our Bronsted-Lowry acid, because remember, one needs to be the acid, one needs to be the base. So the Bronsted-Lowry acid donates its proton and forms a conjugate base. Notice the only difference in these two species is one proton. That's what constitutes a conjugate pair. Now, water, our Bronsted-Lowry base, accepts that proton and forms a conjugate acid. So now we have our species of our Bronsted-Lowry base and its conjugate acid. This constitutes a conjugate pair. Our second reaction isn't quite as straightforward because we don't have water to start with, so we have to identify which species is either accepting or donating a proton. Again, it's only one H plus difference in the two molecules. So here we can take ammonia, NH3, and we can see that it's forming ammonium on the other side of the reaction. That's one proton more. Therefore, ammonia, acting as your Bronsted-Lowry base, accepts the proton, forming ammonium, the conjugate acid. We now have a conjugate pair, ammonia and ammonium. This species must be acting as our Bronsted-Lowry acid, proton donor, and we can see that. the Bronsted-Lowry acid donates a proton and forms its conjugate base. Again, the only difference in these two formulas is one H plus. That constitutes our conjugate pair. So I think we're all familiar with the idea that acids can be hazardous, right? They can eat through metal or corrode objects. They can burn our skin. We could sustain some horrific injuries if we're not careful using certain acids. But at the same time, right, acids are something we ingest on a regular basis. We can see here Lemon Squeezy Face taking a bite of citric acid that's in this lemon, and it's causing that sour sensation on his tongue. So what differentiates some acids being quite hazardous to something that may be mild or something that we might ingest on a regular basis? And it has to do mostly with the strength of ionization, or how much hydronium we form in solution. So let's talk about sort of categorizing acids and bases. We do so by the amount that they dissociate in water. So let's take a strong acid. So by definition of a strong acid, the acid dissociates completely in water, right? We use that single left to right arrow there, just one arrow, right? Which means that once we've put this hydrochloric acid in water, there's no more hydrochloric acid left. It's completely dissociated into chloride anions and hydronium cations. In the case of a weak acid, like acetic acid, it's still going to dissociate in water to form its conjugate base in hydronium, but notice weak, not completely dissociating, meaning we have equilibrium arrows here, meaning that at all times, once we reach equilibrium, all of the species exist. So acetic acid doesn't completely dissociate. Some of it donates its proton to water to form hydronium. Remember, what we really want to measure is the concentration of hydronium of H3O plus in solution to identify the strength of an acid. So let's take a look at the relationship between a strong acid and its conjugate base. So strong acids completely dissociate, forming hydronium in water. What does that mean about the conjugate base that's formed from that Bronsted-Lowry acid that donated its protons? We can see up here in our chart here that strong acids completely dissociate, leaving their conjugate bases. In terms of the reactivity of the bases, strong acids leave negligible bases, meaning these bases that are formed have almost no desire then to accept a proton and go back the other direction. Now, with weak acids, remember, these are acids that are in equilibrium. They don't completely dissociate. So you have some of the Bronsted-Lowry acid and some of the conjugate base in solution together. The stronger the weak acid, and we get stronger as we go up, what that means is that the stronger the acid, the more it pushes equilibrium to the right, the more hydronium that it forms. The stronger the weak acid, relatively, the weaker its conjugate base is. And on the other end, the weaker that Bronsted-Lowry acid is, the stronger its conjugate base is going to be. So an acid that's considered negligible. So in theory, let's take hydroxide. We can write this equation as hydroxide acting as a Bronsted-Lowry acid, water being the Bronsted-Lowry base, and it can donate its proton to water to form a hydronium and the oxide anion. But because this is a negligible acid, right, it doesn't want to donate that proton. In fact, it's not going to donate that proton. This reaction does not happen. The reason is because its conjugate base, oxide, is a very strong base. It really wants to act like a base. What's going to happen is oxide anion, it is such a strong base, it is going to act as a Bronsted-Lowry base in water. It's going to take that proton from water and it's going to form hydroxide. This reaction will take place. And notice it's a single arrow because an oxide anion is a strong base, meaning a single arrow going from left to right, just like we saw when we talked about the dissociation of our strong acids. So let's recap with a couple of problems. Why don't you hit pause, read these questions, write down your answers, and I'll be right back with a solution. So in the case of part A of the first problem, HSO3 minus acting as an acid is going to donate a proton and form a conjugate base. Water therefore must be the base if this is acting as our acid. So it is going to accept the proton, here's the Bronsted-Lowry base, forming its conjugate acid. In part B of this amphibrotic problem, HSO3 minus is acting as a base, therefore it is a proton acceptor. It's going to accept an H plus and form its conjugate acid. Therefore, water is acting as the Bronsted-Lowry acid proton donor. It donates its proton and forms a conjugate base. In the second problem, the first thing that we need to consider is the lithium oxide. Recall, all lithium salts are completely soluble in water, right? So they're going to completely dissociate into lithium cations and oxide anions. This oxide anion is where we get our acid-base reaction from. So dissolving lithium oxide into water really gives us this strong base, oxide, and it is going to act as the Bronsted-Lowry base, accepting a proton from, therefore, the Bronsted-Lowry acid water, forming hydroxide, the conjugate acid of oxide, and hydroxide, the conjugate base of water. Dissolving lithium oxide in water results in a very basic solution because you get two equivalents or two parts of hydroxide ions in solution.